Hi, everyone, and welcome to lesson 12 on uniform circular motion. So we're going to continue with the same learning objective of applying the constant acceleration model to objects in a plane, or which it means 2 dimensions. And this lesson is going to do that with what we call circular motion, and particularly uniform circular motion. So when an object is moving in a circle, it obviously has circular motion. But when it's moving at a constant speed, then we call it uniform circular motion. So that's similar to when we very beginning of the course, when we learned about just uniform, we called it uniform motion, where an object was just moving at a constant velocity. So if an object moves at a constant speed in a circle, then we could just call it uniform circular motion. Right, so I'm going to show you a couple of videos to start with of examples where we see some uniform or any kind of circular motion, really, and then we'll kind of talk about and learn about some things from those videos. So in this one here, I just have a golf ball on a string, and I'm just going to spin it around in a circle. And I tried to create a uniform circular motion, but it's kind of hard to do by hand. But you can see that it is moving in a circle. And what's important about this is that we see that there is a force that's causing it to move in a circle. So it's not just doing it by itself. And so in this situation, we have the force is me pulling on the string, and since this thing is moving in a circle, it has a radius, right? Circles have a radius, and the radius is basically from the distance from the point of where it's spinning to the edge of the circle. And so the ball would be forming the edge of the circle, and that length of the string there between where I'm pulling on it and the ball, that would be the radius. Okay, and so let's take a look now at another one. Right. And so in this one, I'm going to show you some circular motion here. So I got a ball, and I have this circular device, and it's just moving in a circle. So now, whoops. All right, so it's moving in a circle here, and now there's no force coming from the center of the circle anymore. So with the ball on the string, I had a force right at the center of that circle. But we still have a circle. There's still a center to the circle. So there's still a radius to the circle, but the force that's providing the circular or causing the circular motion is this wall here. Okay, so the wall is causing the ball to continue to move in a circle. Okay, but if that force was removed, okay, if I were spinning that ball on the table and the string broke, what would happen to the tennis ball? If part of this wall wasn't here, what would happen? Well, this is a special demonstration where I could take apart, change this wall. So I'm going to open it up, and then we're going to see what happens when. Okay, so it doesn't continue to move in a circle anymore. It now, we say, goes off on a tangent. So that's an expression we sometimes use in English when somebody talks about something that's not directly related to what the conversation is, and they sort of, we say they just go off on a tangent talking too much about one particular thing that's sort of just more of a side thing. And so you'll hear me go off on a tangent a lot. And the reason we call it a tangent is because, well, what do you know about the tangent line from geometry? Well, it's a line that is perpendicular to something, right? We say it's tangent. And so every point on a circle is a tangent line, right? You can draw a tangent line at every point on a circle. So what we see here is that it goes off on this tangent, and we see that it's a straight line, okay? And it's essentially moving at, we see the dots are pretty much evenly spaced apart. And so it's moving at essentially a constant speed. And this is what I was starting to talk about in the projectile motion, when we started seeing that ball that was shot up and then fell back down. And I was saying that there's an independence of the X and Y directions. And so the tendency of something is always for it to continue moving in a straight line at a constant speed, unless it's acted upon by something else, some other outside force that's causing it to do something different. So when we shot the ball up while the car was moving, that little cart was moving, there was an outside force vertically. There was gravity, was that force, but horizontally, there was no other force. So the rule that an object wants to keep moving in a straight line at a constant speed, unless acted upon by another outside exterior force, that's critical, okay? It's actually called the law of inertia, or sometimes we call it Newton's first law of motion. And so we see that here when we break the circle, when there's no longer that force causing, that outside force of the wall causing the ball to move in a circle. Once it leaves, it just moves along in a straight line at a constant speed. And of course, eventually, friction would be the outside force that would cause it to stop moving at a constant speed, okay? If it ran into something, if the ball hit something, it might bounce and go off in a different direction. But for the most part right here, we see that this is very accurate. This is what is supposed to happen to objects. And so that's why we can say in projectile motion that the horizontal speed is always a constant speed. All right, and in reality, we know these are not perfect. There's friction and all kinds of things, but that's part of our study here in beginning physics, is to model things as if they were these ideal situations so that we can make our examination easier. All right, so we have this tangent, all right, that the ball moves off on. And then, and so finally, I'll show you one last video, and maybe some of you have seen one of these at your grandparents' house or something, but it's called a record player or a turntable. There's all kinds of different names for it. They're actually kind of making a little bit of a comeback too. If you go to Target, you can actually buy a vinyl record again. So what I'm going to show you here is when you turn it on, when you turn the record player on, it begins spinning. So initially it has a little bit of acceleration initially, but then it moves at a constant speed. So we'll have some uniform circular motion. And what I did was I put these two little dies, a yellow die and a red die, so that we can kind of compare the motion of a smaller circle to a larger circle. All right, so let's get it started here. And I'm going to move it at the lowest speed the record player goes at. Okay, and then we're going to put some dots, all right, sort of like a motion diagram, to see what's going on. So, oops. I'll hit pause. And so now we're not perfectly above, right? We don't have a perfect bird's eye view the way the camera is, but you could see essentially, right? So we see the acceleration at the beginning, they're closer together, then they start moving further apart. But now, once we do that, we start seeing, all right, the red, the spacing is a lot further. They're essentially equal spacing after it's done accelerating, but and the same thing with the yellow, but the yellow dots are a lot closer together. Okay, so the yellow is actually moving slower than the red, right? So even though there's a constant speed, a uniform circular motion, depending on the size of the circle, or if you're on a two-dimensional plane like this record player is, well, then the further you are from the axis, you're actually moving faster. But you might say, well, what do you mean? Because you're saying that this is constant uniform circular motion, it's constant speed. Well, there's two kinds of speeds with circular motion. We have where we have this uniform circular motion. We have a speed where it's kind of moving through an angle, okay? And we're going to refer to that as angular speed or angular velocity, okay? And so both of them will move through the same angle, all right, no matter where they are on this plane, on the circular plane. But there's something also that they do have a speed that is different, and that's called a tangential speed or tangential velocity. And so like we saw in the previous video, we had an object, when that force was removed, then the object moved off on a tangent line, okay? And so every point, we said every point in a circle has a tangent line. And so every point as an object's moving around in a circle, it not only has an angular velocity, which is constant, but it also has a tangential velocity. And so the angular velocity doesn't matter how far you are from the axis of rotation, but the tangential velocity does. Okay, so we can see the further you are, then your tangential velocity is greater. Okay, and I'll show you. We'll do a couple more speeds here. And so right now there's a force. There's actually more than one force that's causing the object to move in a circle. It's the fact that this record player is actually spinning. This plane is spinning, but there's also, you can see that it's sort of a plasticky, rubbery kind of bottom with some lines in it. So it's got some really good grip, right? Which means friction. Okay, so friction is helping these bottles to stay put and continue moving in that circle. Okay, and then finally, I'm gonna use the highest speed, and we'll see what happens here. All right, and what happened? They literally flew off on a tangent. They went off on a tangent. Okay, so it was, now we got to this point where it's so fast that the friction force is no longer strong enough to help continue these bottles to continue to move in a circle, and so that force was broken, and you'll notice, and we'll put some dots over them now, and we'll see that, right? Well, maybe the yellow one will be better, but it's kind of hard to see that they're moving. But initially you could see that this one, the red one, until it hit the back over here, it went off on a tangent in a straight line. Okay, and the yellow one essentially did the same thing. And so it moved off with that tangential velocity that it had moving around in the circle. And one interesting thing here is to note is that which bottle flew off first? Right, was that red one, wasn't it? Okay, and that's how we can also see that the further you are, the greater tangential velocity is. Okay, it was moving faster, and so even though they were essentially identical masses, the one that was further out was moving at a faster tangential velocity, and so it overcame friction sooner than the one that was closer. Okay, and so you could experience this if you hopefully this summer you can go to an amusement park safely, and maybe you can jump on the merry-go-round, and you'll see that the closer you are to the center, you know, you're moving quite slow, right? You're not. It feels like you're moving slow, and it feels like you're moving faster the further you are out. Although all those horses and whatnot and seats, they're all fixed, right? Nothing is moving at a separate angular velocity. All right. Okay, so we have a radius. Every circle has a radius, right? Like I already have drawn here. And when there's some terminology we use when it comes to a circle. So when we make one complete the circle one full time, we might call that a revolution. Okay, and the amount of time that it takes to complete that full revolution we call a period. Okay, so period is essentially the time interval, right? Like a delta t. How long does it take for one full revolution? Okay. And we have a special notation for when we're in a circle. So we know that time interval, we've been using delta t. Well, for period, we use just a capital T. Okay, that's how we represent period. Okay, and so we know that velocity is the distance traveled, which we called x, over the time interval. So what is the distance traveled if an object moves in a circle? So if it moves and goes one full rotation, okay, we might say, well, you know, displacement would say it ends up right back where it started, so it's zero. But we're not dealing with displacement yet. And it's going to be a little bit different here for circular motion. But essentially, what is this distance that's traveled? Right? It's the circumference of the circle. And what is circumference? Right, circumference, hopefully I spelled that right, is 2 pi r. Right, 2 pi times the radius. So that's the distance it would travel in one full revolution. So for this speed here in uniform circular motion, it would be 2 pi r over the period. Okay. So we would say so it's moving at a constant speed if it's uniform circular motion, and we know that at every point on a circle is a tangent. And so if we wanted to know the instantaneous velocity, right? That would also just be, all right, if we wanted to know what's the instantaneous velocity here, well, it'll just be the tangent there. And since since circular motion, it's the same everywhere, well, then every tangent line off the circle for a tangent velocity vector is going to be the same. Okay, and so the velocity vector really only has a tangential component. It has the same, if we were to draw it as an arrow, if we were to represent it as an arrow, the arrow would be the same length everywhere. Okay, and so when we calculate velocity or speed like this is really our tangential velocity. And so you probably will usually see it as with a subscript t underneath there, v subscript t. Okay, so let's try an example of some uniform circular motion. So in your car, you probably have one of these meters that says the one, times 1,000 RPMs on it, and it's called a tachometer, and measures the spinning of the crankshaft in your car. So what we can determine, what's the speed in meters per second of a crankshaft if it has a diameter of 10 centimeters, and maybe it moves with a speed of 3,000 RPM. So that would mean the needle would be pointing at the 3 there. Okay, well, we're given RPMs, that's revolutions per minute. Okay, so if we're looking for its speed, okay, we're looking for essentially its tangential speed, and so that means we have to figure out what is its period, right? Because tangential speed is 2 pi r over the period. Okay, so what's the period? Okay, well, we're given 3,000 revolutions per minute. That's something that's a quantity we call frequency. Okay, so you've heard the term frequency before, and frequency is essentially how many times something happens per second. Okay, so often you'll hear about the unit hertz. Okay, so most TVs have the picture is in 60 hertz, which means that, and we've talked about this before, that it's essentially 60 pictures are being taken per second to make it appear to our brain to be an actual moving picture, a video, right? But it's really not. It's just a series of pictures that are happening so fast we can't tell. So, so we're given, this is 3,000 revolutions, right, per minute. Oh boy, doing that. So first of all, we want to know the speed of meters per second. So we're going to have the first thing is to change this minutes to seconds. Okay, and then we'll give us 50 revolutions per second. Okay, and so that's the frequency. And frequency we symbolize with a lowercase f. Okay, so that's how many times. So basically, the crankshaft spins 50 times each second. And so there's a simple relationship between frequency and period. They're just the inverse of one another. Okay, so basically, if we wanted to know period, it's just 1 over the frequency. So this would be 1 over 50, which would be 0.02 seconds. Okay, and so the revolution is not exactly a unit. It's just saying, the hertz The frequency is just a measure of how many times anything happens per second. Okay, so now we have the period. So the tangential velocity, 2 pi r, right? So r is the radius. This is an important part to think about, because a lot of times you'll need to use radius, and not just for circular motion, but for a lot of stuff that has to deal with circles. Then a lot of times it'll give you the diameter, right? And I see this happen over and over and over, and I even make the mistake too sometimes, is that you'll forget to turn that diameter into a radius. So we wouldn't want to put 2 pi times 10 centimeters here. We'd want to put 5 centimeters. Okay, so that's this very easy mistake to make. So try to be conscious of that. And since we want to keep things in SI units, well, we'll turn that 5 centimeters into 0.05 meters. We have some consistent units. Okay, so the tangential velocity is going to be, I got 15.7 meters per second. Okay, which were the units that we wanted to know for them to be in. Okay, now, so there's some similarities between linear motion and circular motion, and so if we think about, so we've already figured out 2 pi r is a circumference. So like if you were to roll a tire one full rotation, and maybe you put some paint on it or something so that it made a line, it would actually make a line, right? Straight line. And the length of the line would be the circumference of the tire. Right? So we know that that's 2 pi r. And so like with linear motion, we were able to describe the position of an object during uniform motion. Well, we could do the same thing for an object in uniform circular motion. And so the way we do this is by describing the angle with respect to the positive x-axis. And so we did that previously when we reviewed trig and all that, to try and describe how do we describe the angle or the direction of a vector. Okay, so what I'm going to start off by doing is I'm going to place this circle on a, get it straight, on a coordinate plane. Okay, so I'll make a coordinate plane where the x and y axes go straight through the center of the circle. Okay, so we have x and y. Okay, and we know that for a full revolution of a circle, one revolution is, we can describe that in terms of degrees. So we know there's 360 degrees in a circle. We can also describe it in terms of radians. There are 2 pi radians in a circle. Okay, and using radians is helpful because it allows us to relate the angle of the displacement to the arc length. Okay, so if you recall from geometry, arc length we call with a letter S for whatever reason. And so using the radians, we can relate the angle to the arc length. And if you recall, the relationship is S equals R theta. So then, like linear motion, we can have, in circular motion, we can have angular displacement and angular velocity. And so we can say angular displacement, we can say it's delta theta, right? So before we had delta x, it would be theta final minus theta initial. So maybe on this little piece here, we would have theta initial might be right there when it's on the right on the positive x-axis, and maybe this is theta final there. Okay, and so we'll go through an angular displacement of delta theta. Okay, so then angular velocity, right? If we could do an average or a constant. Well, then angular velocity, we use a different symbol for angular velocity. Looks like a W, but it's actually the Greek letter omega. And so then that would be angular displacement, the delta theta, over the time interval. Okay, and we can find the instantaneous angular velocity because it's just the tangent at any point on a circle. And we know to find that, like we've done previously, it's the limit as delta t approaches 0 of this delta theta, delta t, right? And that is just the derivative of theta with respect to time. And so direction, to define direction, since we're moving in a circle, we just keep that repetitive motion over and over again. Like how we measured angle from respect to the positive x-axis, well, positive, we consider positive to be counterclockwise because that's sort of like how we start counting degrees. 0 is here, go up to 90 there, and so on. So positive, so counterclockwise is positive. Okay, and so then negative direction would be if it moved clockwise. Okay, and so if the angular velocity of the object is constant, well, then we have uniform motion. And so it technically would not be constant angular velocity because remember that velocity is a vector quantity which has magnitude and direction. And so the direction is constantly changing. And so we're going to get into that in just a little bit, how we deal with that. Okay, and so like with linear, the displacement, position, displacement, velocity, well, we can also graph angular position and velocity, okay? So if we have a constant angular velocity, well, then on a angular position versus time graph, it's going to look like a straight line, right? Like we've seen before. And then the angular velocity versus time graph, since it's a constant velocity, well, that'll be that flat line. Okay? And so again, the slope of the position versus time, in this case, it's just an angular position. Well, the slope will give us the angular velocity. And the area under the curve of the angular velocity versus time graph, that will give us the displacement. Okay, so nothing a whole lot new. It's just applying this to to angular or circular motion. And so we came up with a relationship where we could determine where a final position of an object would be after it was moving for a certain amount of time at a constant speed. And so we could do the same thing for angular velocity. So we can say that the final angle will be the initial angle plus that constant angular velocity and the time interval of however long it's moving at that constant angular velocity. All right, so we said that there's 360 degrees or 2 pi radians in a circle, and so this picture here, this diagram kind of shows you. So the positive x-axis, that would be 0. Initially, it would be 0, right? And then it would go, when you made full circle, it would be 2 pi. Okay, and so 90 degrees corresponds to half pi, 180 degrees to pi, and then 270 degrees to 1.5 pi. And so in the uniform circular motion, if we wanted to find, well, what's the corresponding degrees to radians, because we can describe circles in degrees or radians. Well, the displacement of a full revolution, right, delta theta, would be, a full revolution would be 360 degrees or 2 pi radians. Okay, and then the time interval we described as the period, positive t. So we can actually describe this angular speed, right? So before we learned about tangential speed. Now we can really define the angular speed. So we can say it's this distance, the displacement, 2 pi radians over the period. Okay, and we could put magnitude bars there if we want to, because we know we really can't. It's not really going to tell us a whole lot about direction, whether we get negative or positive, right? We're going to need to think about whether we're moving counterclockwise or clockwise. Okay, so we noticed that it has nothing to do, angular speed has nothing to do with the distance, with the radius, with the distance you are from this axis of rotation. Whereas the tangential velocity, it did. All right, so let's say we have a ball rolling around a circular track and it has an angular velocity of 4 pi radians per second. Can you determine the period of the motion? So if we want to pause for a moment and give that a try, you can. All right, so we know that the angular velocity, that omega, is the 2 pi radians per period. And we know that our angular velocity, our omega, is 4 pi radians per second. And so if we solve for t, that'll just be 2 pi radians over 4 pi radians per second, which would give us 0.5 seconds. Okay, and you can also think of it logically too. If you're moving at 4 pi radians per second and a full revolution is 2 pi radians, well, we can see there that there was 2 full revolutions in 1 second. All right, so it went through 2 times in 1 second. And that was how fast, that was its frequency. It was 2 times in 1 second, and period is the inverse of the frequency. So 1/2, 0.5. So we had tangential velocity. Every point on the circle was a tangent, and it was 2 pi times the radius over the period. And so we can write this, we could also write this in terms of angular speed, right? Because we know that angular speed is 2 pi radians over period. And so that's what we have. We have the 2 pi radians over t there. So essentially, if we substitute that in, we could say, well, that's just omega, right, times r. All right, so we could say tangential velocity is also omega times r, which is also tangential velocity. Here's also dependent on the radius, which we know it should be. Right, and so we know that we said that we're moving in a circle. We have a uniform motion, but technically the direction is constantly changing because we're moving in a circle. So it's hard to really call that a velocity. Well, what is the cause of an object moving in a circle? Well, it's moving in a circle because there's got to be some force causing it to do so, and since the velocity is changing, what do we know? Velocity is technically changing. And we know that a vector needs magnitude and direction. Well, we know we've been looking at its magnitude. We know that its magnitude is constant. And so the only reason for the only way that this could still be a vector quantity is if the direction is changing, which it is. And so the reason for this change is that there is an acceleration. Okay, remember with acceleration, you can have a constant velocity, but the direction has to be changing. So what is the acceleration? Well, sometimes we call this centripetal acceleration. Okay, and the word centripetal literally means center seeking. And so there's an acceleration that's always pointing toward the center of the circle. Okay, so everywhere is pointing toward the center. Right? So even though we're moving at a constant velocity or constant speed, but our direction is constantly changing, we are technically accelerating. So if we look at a car going around a curve and it's moving at a steady 45 miles per hour, can we say, is the car accelerating? Well, yes, it is, because acceleration is a vector quantity, which requires either the speed or the direction to be changing. And since it's going around a curve, that direction is constantly changing. Okay, so which of these vectors would show the direction of the car's acceleration? Well, it would be B, wouldn't it? Sounds weird. I think it's going to take a little getting used to, but it's technically accelerating toward the center. Okay, because going around a curve is just partially going around the circle. All right, so how do we find centripetal? How do we calculate centripetal acceleration? Well, what is acceleration? It is the change in velocity for the change in time, or that's the derivative is dv dt. Okay, so what is dv? Well, we know here that from the circle we have this angle theta. We have this radius r and this arc length s. All right, and so dv is a change in velocity, which is it's not changing, but so how do we deal with that? Well, we know the velocity is tangent. Okay, so we have a velocity there. So at this point on the circle, but then if we get to say this point on the circle, it's also going to have a tangential velocity vector, okay, equal to the first one. And there's also going to be a distance here. Right? So these two will form an angle that is equivalent to this angle. Hopefully that makes sense. And so these are our velocity vectors right here and here. And so just like this, how this is the angle, we could call it, we say it's s equals r theta. It might be more appropriate to say ds equals r d theta, right? Because we're going through a displacement, a d theta, an angular displacement, which will allow us to go through a linear displacement, ds. And so if those are two similar triangles, then we have this theta, we have v are the sides equal in length, so just the same thing is going on here in this wedge. Well, then this side is dv, the change in v. So what is dv? So according to the same pattern here, s equals r theta, well then dv will equal v d theta. Okay. So what is dt? Velocity, right, is a ds dt. Right, so how long it takes to go through this s length, and we know that s equals r theta. So this could be d r theta dt, which that r is constant, so I can pull that out of the derivative. Okay, and so then dt, if we rearrange, is then r d theta over v. Okay, so I could put that over here now. And what do we see is that our d thetas cancel. Our v move up to the numerator, that'll give us v squared, okay, over r. So the acceleration is, the centripetal acceleration is v squared over r. Okay, so this is in terms of, this is technically the tangential velocity. Okay, a equals v squared over r. We could also write this in terms of angular velocity, because we know that tangential velocity is omega r. Okay, so then v squared over r would be, right, omega squared r squared over r. So one of those r's will cancel, and we're left with omega squared r. Okay, so we can find the angular acceleration in terms of tangential velocity or angular velocity. All right, so let's try a couple situations thinking about this, and also we saw this happening, a similar kind of thing happening in the video with the dies on the record player. Well, let's say we have Cardi B and her daughter Culture are riding a merry-go-round that's spinning steadily. So we have a uniform circular motion. And let's say that Cardi B is twice as far from the axis of rotation as Culture is. So how does Cardi B's angular velocity compare to that of Culture's? Okay, so angular velocity, recall, is 2 pi radians over the period. Okay, so angular velocity only depends on the period, right? How fast or the angle through which we're moving. So how long does it take to complete a full revolution? So it has nothing to do with where you are on the plane, okay, on the merry-go-round. So it will be B. They're gonna have the same angular velocity. Okay. Now let's say that they're on the merry-go-round, same situation, but now we want to know how does Cardi B's speed compare to that of Culture's? Okay, so if we're saying we're not saying angular speed, we're saying just speed. So this is essentially telling us, right, tangential. Okay, we know that tangential, we learned, was dependent on 2 pi radians times the radius over the period, or omega times the radius. Okay, so it does depend on radius now, the tangential speed. And so since Cardi B is twice as far from the axis, okay, the r, the radius is twice as big, well then the tangential speed is going to be twice as much. Okay, and then finally, same situation, how can we compare their accelerations? So we said that acceleration is v squared over r. Okay, and that's the vt squared. Right, so we know that Cardi B is twice as far. We said that her tangential speed was twice as much. So what I'll do here is I'll say that this is well, it's going to be 2 times bigger, but it's squared, so it's going to be 4 times bigger, and it's also divided by the radius. So she's got twice the radius. So that's 4 over 2. So it ends up being the acceleration is only twice as much. All right, so these are the problems in the homework related to this uniform circular motion. I have one extra example problem if you want to look at that. And so, did you learn to apply the constant acceleration model to uniform circular motion? All right, well, we learned about tangential velocity. Okay, and that should be a t there, subscript t there. So we saw we could do it in just in terms of 2 pi and a period, but we could also put it in terms of angular velocity as well. Okay, and we also put acceleration in terms of tangential velocity, t there again, and an angular velocity. All right, so that's all for lesson 12.